Okay, at this point you should be very comfortable with taking derivatives of polynomial functions. So the next thing we start to look at are functions that are comprised of products or quotients. And so we look at first the product rule. Now, when it comes to the product rule, we saw constant multiple rule. You can pull constant multiples outside of a function and then take the derivative. This is not what this is talking about. This is saying I have two functions of x that are differentiable functions, and I'm looking at the product of those two functions. So f of x times g of x. So this would apply to something where I have something with x's in it times something else with x's in it. Here's a prime example of that kind of function, and I want to take its derivative. The common mistake that people think they can make is that they say, well, let me just take the derivative of this, let me take the derivative of this, and multiply those two answers together. That's not how this product rule works. In that, if you think about it, let me give you an easier example. If we said y equals x plus 2 times x plus 3. As a function, that is x squared plus 5x plus 6. Then, if I wanted to take the derivative of that using my basic rules that we already learned about polynomials, I would say the answer is 2x plus 5. Now, thinking of, if I just took the derivative of this piece right here, rather than looking at this, I'm going to look at this. If I just took the derivative of this piece right here, that derivative would be 1. If I just took the derivative of this piece right here, that derivative would be 1. And 1 times 1 certainly is not 2x plus 5. So just taking the derivative of each one of these pieces, if it was legitimate to do that, I should get the same thing as if I take the derivative of this function, because these are the same function, they're equal, just different forms. When I take the derivative of this piece, this function, I get this. If I try to just take the derivative of the individual pieces here, I would get 1. So that doesn't really work. So how can I do this? Well, the product rule tells me exactly what I should be doing. So what it says is, I have two functions. Let's think of this one as the first function and this one as the second function. It says what I should do is take the derivative of the first function and multiply that by just the second function without a derivative. Then I should take the derivative of the second function and multiply that by the first function without a derivative and add those things together. Now, seems like a lot, but derivative of first times the second plus derivative of second times the first. And so what you start to get here is looking at how we would get 2x plus 5 if we use this. So if we use this and I say, okay, let's take the derivative of the first piece. The derivative of that is 1. But rather than just having 1, I'm going to multiply that by x plus 3, which is the second function. Plus, I'm going to take the derivative of the second function, which is 1. And I'm going to multiply that by the first function, which is x plus 2. Now, 1 times x plus 3 is x plus 3. 1 times x plus 2 is x plus 2. X plus 3 times x plus 2 is 2x plus 5. And you see, that does give us what we would have gotten when we took the derivative of this form. So this product rule works for this example. Now that doesn't mean it's going to work for every single example, but in using the limit definition, we can see that this is in fact the rule that would work for all product functions. And so something you're going to have to get used to is how to apply the product rule and knowing what function you're taking the derivative of when. So you're going to have to commit this product rule to memory. Another way to think about it is by using prime notation. And so it's just the same thing, just a simpler way to write down what this is saying. So if it's f times g prime, it's f prime times g plus g prime times f. First function derivative times the second plus the second function's derivative times the first. So if we use that for this example, and I want to take the derivative, I should take the derivative of 2x plus 5x squared times 3x minus 7 plus the derivative of 3x minus 7 times 2x plus 5x squared. And that should get me what I'm looking for. So that's telling me exactly how I should apply this derivative rule to this problem. Now I have to actually do it. So I need the derivative of 2x plus 5x squared, which at this point should be very easy. It's going to be 2 plus 10x times 3x minus 7 plus the derivative of 3x minus 7, which would be 3 times 2x plus 5x squared. And that is my derivative. Y prime equals this. I'm done taking the derivative, but that's not the answer I'm going to write. We can do better than that. We can simplify this answer, but as far as taking the derivative, that's it. Now, algebra tells me I should probably multiply this out, collect like terms, make this as simple as possible. So I'm going to get 6x plus 30x squared minus 14 minus 70x plus 6x plus 15x squared. X squared gives me 45x squared. Negative 70x plus 6 gives me what? Negative 58x. And then I have this minus 14. So that is the simplest version of the derivative. But from here down was all just about simplifying using your basic algebra skills. What we could have done is from the beginning, we could have just multiplied this out first before we took the derivative, in which case we would have gotten, I don't know, what would this be, 15x cubed. That would have 15x cubed. We would have gotten negative 35x squared plus 6x squared, so it would be negative 29x squared. And we would have gotten negative 14x. Is that right? Negative 14x, yes. This would be a 14 down here. That's the original polynomial just multiplied out. Then took the derivative of this. Using what we know about polynomials, you would have arrived at this answer just as well. 3 times 15 would be 45, x squared. 2 times 29 would be 58, x to the first. And this will just give you 14. Negative, obviously negative here and here. So you don't necessarily need the product rule for this problem, but you could apply the product rule and still get the same answer. Okay, here's another one. Again, we could attack this problem multiple ways. One thing we can't do is just straight apply the power rule to this, because the power rule only applies to x to a power. This is 2x minus 1 to a power, so it's a little more involved. Eventually we'll figure out a way to tackle this using some form of the power rule. We're going to call that the chain rule, but for right now, we don't have that. So what we're going to have to do is either write this as 2x minus 1 times 2x minus 1 and use the product rule, or multiply all this out and get 4x squared minus 4x plus 1 and just take the derivative of the polynomial. Now probably that's the easiest one, but to get practice with the product rule, we're going to take the derivative using the product rule. So we're going to take the derivative of 2x minus 1, which is the first piece, and multiply it by 2x minus 1, which is the second piece, plus we're going to take the derivative of 2x minus 1, which is the second piece, times 2x minus 1, which is the first piece. Now, it just so happens they're all the same, but think of it as first function, second function. Derivative of 2x minus 1 is 2 times 2x minus 1, plus derivative of 2x minus 1 is 2 times 2x minus 1. So we have 4x minus 2 plus 4x minus 2, giving us 8x minus 4. If you look at this, you should easily see that the derivative of this is 8x minus 4. So whether we use the product rule or we just multiply it out and take the derivative of polynomial, we would both get the derivative to be 8x minus 4. Really should be no problem here. On the test, I really don't care which way you do it. Here's another example. Now on this one, I'm not really going to use the product rule. I'll show you how it would be done with the product rule, but I wouldn't expect anyone to use the product rule for this one. Now you think of it as a product. 3 is the first piece, 5x squared plus x plus 3 is the second piece. But it's not just any old product. This is a constant multiple product. And if we apply the constant multiple rule instead of the straight product rule, what the constant multiple rule says is that the 3 should come out And I really should just take the derivative of 5x squared plus x plus 3, which would give me 3 times 10x plus 1, which I could write as 30x plus 3. Real simple. Now let's say for some reason you thought maybe I should use the product rule, which will work. It's just a longer way to get this done. And you took the derivative of the first piece, which was 3, times the 5x squared plus x plus 3, plus the derivative of 5x squared plus x plus 3 times 3 itself. What you're going to see is that the derivative of this is going to be 0 times 5x squared plus x plus 3, in which case this whole piece is just 0, plus then we have this. Well, that is the derivative of 5x squared plus x plus 3 times 3 itself, which is exactly what we did here. And so if it's 0 plus this, it's essentially just this piece, and that piece's derivative would essentially give you in the end 30x plus 3, just giving you that as your answer. But this is the far longer way to think about it. If you recognize that this is a constant multiple and not two functions that have x's in them multiplied together, you could realize that product rule is not really necessary. While it can be used, it's not necessary. Okay, so if we do one more, if we said, how about we go with y equals 400 times 15 minus x squared times 3x minus 2. And say I want to take the derivative of this. So if I want to take the derivative, y prime, you look at this, I have three things multiplied together. 400 times 15 minus x squared times 3x minus 2. And so looking at this, you got to recognize that the 400 is a constant multiple. So that 400 is going to come out. And then I'm going to take the derivative of this part. Well, that's a product. So I'm going to take the derivative of the 15 minus x squared times 3x minus 2 plus the derivative of the 3x minus 2 times the 15 minus x squared. And that whole thing will be multiplied by the 400. So I have 400 times negative 2x times 3x minus 2 plus 3 times 15 minus x squared. So I get 400 times negative 6x squared plus 4x plus 45 minus 3x squared. So and then I get 400 times negative 9x squared plus 4x plus 45. And so that's my derivative. Now, if you want, you can then additionally multiply the 400 in now, or you could leave the 400 out as a constant multiple. It really doesn't matter. This answer would be more than acceptable. Okay, now we move on to the quotient rule, which has a very similar setup. Instead of taking the derivative of a product, we're going to take the derivative of a quotient. It's a little more involved, and the algebra of it is definitely what will get most people. So thinking about what it says first, if f and g are differentiable functions and we're looking at the quotient f of x divided by g of x, this is how we're going to take the derivative of f of x divided by g of x. We're going to take the derivative of f of x, which is the numerator, by itself. Then we'll multiply that by g of x, which is the original denominator, minus the derivative of g of x times the original f of x, which is the numerator. Now, if you think about it, that setup has a very common feel to the product rule. Now, the product rule, we had addition here instead of subtraction. So here, order is going to matter far more than it did before. But nonetheless, it's got a very common feel to it. But then there's this additional part. And the additional part is that we take that and we divide that whole thing by g squared, which is just take the original denominator and we're going to square it, and that's going to be now the denominator of our derivative. If you want to look at it a little bit simpler in terms of notation, f over g prime is going to be g times f prime minus f times g prime all over g squared. You're taking the derivative of f, you're taking the derivative of g, one at a time, and this whole thing is then the derivative of the quotient. So what you can't do is just take the derivative of the numerator, just take the derivative of the denominator, and then divide those two answers. It does not work that way. This whole process is how we take the derivative of a quotient like this. So let's see how it works. So this is my numerator, this is my denominator, this would be what this represents, this would be what this represents. So in taking the derivative, I should take the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator all over the denominator squared. So now I have to actually do that. That's just writing out what this tells me to do. Now it's a matter of doing it. Well, if you look, there's really only two derivatives we're going to do here. And this whole thing will then be the derivative of the quotient. We have to do this derivative and this derivative. So derivative of 3x plus 2 is 3 times x squared minus 5 minus the derivative of x squared minus 5 is 2x times 3x plus 2 all over x squared minus 5 squared. So for all intents and purposes, this is our derivative, but not the answer we want to give. There's a simpler answer. We could simplify this, but as far as taking the derivative goes, we are done taking the derivative. So now I want to simplify this. What I'll see a lot of people do is they go, oh, here's x squared minus 5, here's x squared minus 5, let me cancel them. No, you learned in algebra that that can't happen. This minus means that this one's not a factor. Don't cancel it. What we're going to do is distribute this out, distribute this out. So we're going to have 3x squared minus 15 minus 6x squared minus 4x all over x squared minus 5 squared. Once that's distributed out, then I can bring like terms together. And I would have, what, negative 3x squared minus 4x minus 15 all over x squared minus 5 squared. And so there's your derivative in the simplest form for f, applying the quotient rule. So here's another quotient. Now, this one has multiple ways we can get this done. We saw that when we did the product rule. One thing we could do is we could try and multiply out the product first and then take the derivative, and then we wouldn't have to use the product rule at all. Well, sometimes that applies to the quotient rule too. The quotient rule can be applied to this, in which case I could take the derivative of the numerator and the derivative of the denominator and work that into my quotient rule process. But I could also rewrite this function. Since this is a monomial is a single term, this thing simplifies really nicely. 12x cubed over 7x minus 2x squared over 7x plus 5x over 7x. This is just the original function still. A couple of mistakes here. One, g of t. This needs to be an x. G of x, these are x's, so this should be x. Or if this is a t, these should all be t's. So let's change this to an x. Okay, so g of x. So anyway, back to the problem. So this is the same as the original function still. All I did was take this, this, and this, split it apart into 3 separate fractions. It's still the same as the original, because if you think, if I was to subtract and add, they'd have to have the common denominator, and I'd put this numerator all over this common denominator, and I'm just splitting it back apart. But what that allows me to do is to simplify this fraction into 12 over 7 x squared minus this one would be 2 over 7 x to the first, and this would be 5 over 7. I'm canceling the x's using basic exponent rules. So now what I want to do is say, is this easier to take the derivative of, or is this easier to take the derivative of? I would say this one. Now, no matter which one we use, we should get the same answer in the end, and so we will. And what I'll do is I'll take the derivative of this one first using the quotient rule, so we have practice using the quotient rule, and then you're going to see real quick that this will give you the same answer. So let's make some space here, look at this clear. So if I'm taking the derivative of g of x, I'm going to take the derivative of 12x cubed minus 2x squared plus 5x times 7x minus the derivative of 7x times 12x cubed, sorry, minus 2x squared plus 5x all over 7x squared. And so you look at this derivative is going to give me 36x squared minus 4x plus 5 times 7x minus 7, which is this derivative, times 12x cubed minus 2x squared plus 5x all over 7x squared. I could write that if you want 49x squared. Now, what you see is that the next step would be to start distributing this in here, distributing this in here, and you're going to start getting larger and larger values, which you should be able to work with, but we can avoid it. This is my derivative, but not the simplified version. Oftentimes in simplifying, the whole point is you're trying to make things easier. Well, if you're trying to make things easier, you would like to not work with larger values. So what we're going to do here is we're going to take this and see that we have a 7 and a 7 as factors of each one of these pieces. I'm going to factor that 7 out. In factoring that 7 out, now this 7 is gone and this 7 is gone. So what do I have as x times this? Well, now I don't have those large numbers. What do I have? I have 36x cubed minus 4x squared plus 5x. And then here, that 7's gone, so just the negative has to distribute in here, so I get negative 12x cubed plus 2x squared minus 5x all over the 49x squared. Now what you see is that this 7 is a factor, and I can cancel with one of these 7's in the 49. What I can also do is start bringing together like terms. And so what I end up with is 24x cubed, that's the 36 and the 12. And then I'm going to have negative 2x squared, which will be the negative 4 and the 2x squared. And the 5x and the minus 5x cancel all over 7x squared. Now I can still do one better. These have an x squared in common. So if I factor an x squared out of that, I have 24x minus 2 all over 7x squared. Now these x squareds can cancel, and I'm left with 24x minus 2 over 7. So there's my derivative. But remember, let's take a look at what we had going on over here. If I just use this one, these are subtracted. It's not a quotient because this is a constant multiple, this is a constant multiple, this is a constant. In which case I'm just going to do like this, a polynomial. The 2 will come out to the front, and my derivative would be 24 over 7x. This one, the derivative of x is 1, so minus 2/7. And this derivative is 0, so it's gone. So if you look at what you have 24 over 7x minus 2 over 7. We'll put that together, 24x minus 2 all over the common 7 denominator, and you get the same thing. This was a lot easier, but I had to recognize that this could be written this way. And that all has to do with this monomial here. The previous example, the denominator was not a monomial. You know, if you have a denominator that looks like, I don't know, x squared plus 3, that's not a monomial. This doesn't work out as well. But if it's just a single term in the denominator, this splitting up works pretty well. Okay, here's another problem. Now we're going to use the quotient rule, but this problem really deals with finding the equation of the tangent line, which is the question that we would have dealt with from the beginning about the slope of the tangent line, etc. But we know that the slope of the tangent line is the derivative. Regardless of what this function looks like, in order to find the equation of the tangent line, I need the slope of the tangent line. Well, the slope of the tangent line is the derivative of the function. So I want to take the derivative of this function. Now, in order to do that, I'm going to rewrite the function. I'm going to write it as 1 plus x to the negative 1 over x plus 1. I'm just going to take this and write that as x to the negative 1. Now I did that because it's easier. It's easier for me to take the derivative. Yes, I still need to use the quotient rule, but in quotient rule, this is much easier to take the derivative of than this is, because I can use power rule. So if I go to take the derivative of the numerator is going to be negative x to the negative 2 times the denominator minus the derivative of the denominator is 1 times the numerator all over the denominator squared. Now, in previous two examples, we've had to simplify this. Now think about it. If I simplify this and I get step, 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 and I get some final answer, what do I really need to do? What I need to do is I need to find the slope of the tangent line at this value. So what I'll have to do is the x value for this point is 1. And I would have to take that and I have to find f prime at 1 so that I could find the slope of the tangent line at that x equals 1. Or we could say at 1, 1. Either one, whether I write it this way or this way, means the same thing. Well, if I have to find f prime of 1, if this is f prime, and this is also f prime, then does it matter whether I plug 1 into here or I plug 1 into the simplified version? The answer is no. I'll get the same answer. So I'm not going to waste my time simplifying this derivative if all I'm really looking to do is to plug a number into it. Now, sometimes we need to simplify the derivative because we're going to use the derivative to do more, but right now, for this example, I'm not going to. It's not necessary. So I want to find f prime of 1. So I have negative 1 to the negative 2 times 1 plus 1 minus 1 times 1 plus 1 to the negative 1 all over 1 plus 1 squared. I mean, the good thing is that 1 to any power is going to be 1, even if it's negative. So this is going to give me negative 2 minus 2 all over 2 squared. So I get negative 4 over 4. So I get negative 1. So this is the slope of the tangent line at 1, 1. Now to write the equation of the tangent line, I have to say, well, y minus y1 equals m times x minus x1. M is negative 1. The point is 1, 1. And so what I get is y minus 1 equals negative 1 times x minus 1. So y minus 1 equals negative x plus 1. Add this 1 over here, and I get y equals negative x plus 2. So this is the equation of the tangent line at 1, 1. Now typically when we're looking at taking the derivative, we want to make sure our derivative is simplified as much as possible. But that's not always 100% necessary. We saw in the last example that we just needed to find the value of the derivative at a particular location. So if we're just looking to find the value of the derivative at a particular location, then we really don't need the simplified version. We just need to know what that value is for the derivative or for the slope or whatever we wanted to describe. And so there's no need to really simplify it. But sometimes you do need the simplified version, and that's because you're going to use the derivative to do something else. And in this case, we're going to use it to find what we call higher order derivatives. So we've seen that the derivative of one function is really another function. And that's the reason why we use this notation, f prime of x, to really further hit home that the derivative is a function in itself. It's just a function that is related to the original function. And so if this is a function, then I should be able to take the derivative of this. And the derivative of this should be what we call the second derivative of the original function. And then I should be able to take the derivative of that, and that'll be what we call the third derivative. You notice in terms of notation for prime, all I'm doing is stacking up these dashes. Now at some point that gets to be a little bit ridiculous. So after we pass the third derivative, we use a parenthesis. And so f parenthesis 4 means fourth derivative, and that is the derivative of the third derivative, and the third derivative is the derivative of the second derivative, and the second derivative is the derivative of the first derivative, and that was the derivative of the original function. But notation-wise, we use the parentheses. And after that, we could say the nth derivative is, again, this notation. So this is still considered prime notation, even though we're not using the dashes anymore. Because if I did something like this for the fifth derivative, that would be a little ridiculous. So prime notation, okay? Then we also have Leibniz notation. So this is Leibniz notation for first, second, third, fourth, fifth. Notice these are not really powers. It's not the third power of the first derivative. This is purely just a notation for the third derivative. I'm not taking the first derivative and cubing it. This is notation for the third derivative, fourth derivative, and this just continues on. There's no real reason to change it because we're just using the number to denote the power. And so you see it a little bit better. Let me erase. So take a closer look to why we have this here. We could use this operator notation, but we're not going to. We talked about how we're really not going to see that notation right now, but we could in the future. It is used in further mathematics. If you look, we kind of just denote this as almost like a power, but it's not. This d to the second, this 2, is really describing this second derivative. Okay, but we'll focus more on prime notation and Leibniz notation. So second, third, fourth, fifth derivative. What's happening here? Well, if we kind of describe what's happening here, take a look at this. What we have is we have a function. That function is, say, f of x. Okay? I don't know if you can see that. F of, let's do it a little bit better, f of x. Okay? And so what happens is the derivative f prime tells me how this function is changing. Okay? So this function tells me how this function is changing. Now, the derivative of that, which would be the second derivative, tells me how this function is changing. Well, think about what this represents. I have a function. This derivative is the slope of this. Okay? But that slope can be different from one location to the next to the next. So I might ask myself, well, if the slope is changing, how is the slope changing? So this function, which is the second derivative, tells me how the slope is changing. Okay? So that's the second derivative. Second derivative describes the change in the first derivative. The first derivative is slope. The second derivative tells me how the slope is changing. And then I can continue on. The third derivative tells me how the second derivative is changing. The fourth derivative tells me how the third derivative is changing, etc. At some point, it kind of gets a little ridiculous when you start talking about it in that regard. We could use all these multiple derivatives to do other things, but as it relates to slope, I think once you get past the second derivative, it doesn't really have a whole lot of meaning as it refers to slope of the original function. In some ways, because we're getting so far away from the original function. But the idea is every time you take the derivative of a function, that tells you the change in the previous function, the function that you took the derivative of. All right, so I could ask you to find the second derivative for this function. That's what this is asking me to do. This is notation for second derivative, and this is my function. In order to find the second derivative, I need to find the first derivative. So in looking to find the first derivative, I would say, well, this is a quotient, so I'm going to use the quotient rule. So my first derivative would be the derivative of the numerator, which is 1, times the denominator, minus the derivative of the denominator, which is 1, times the numerator, all over the denominator squared. Simplifying, I would get x plus 1 minus x plus 1 over x plus 1 squared, which would give me the x's to cancel and give me 2 over x plus 1 squared. Then I want to take the derivative of that. Well, once we learn the next rule, which would be chain rule, we'll have an easier way to do this, but for right now we don't have that. So I'm going to write this as 2 over x squared plus 2x plus 1. That's this squared. I do that mainly because this is the easiest form of this denominator to take the derivative of. And so then if I'm going to take the derivative of that, I'm going to now have the second derivative, which would give me the derivative of the numerator, which would be 0 times x squared plus 2x plus 1, minus the derivative of the denominator, which would be 2x plus 2 times the numerator, all over the denominator squared. Well, this is 0 times that, so that's gone. This will be minus 4x minus 4 over this squared. But remember, this was this. So if I take this x plus 1 squared and I square it again, I really have x plus 1 to the fourth. And then what do I have? Well, I want to simplify. If I pull out a minus 4, I have x plus 1. Here I have x plus 1 to the fourth, which is the reason why I wrote it this way. This x plus 1 and one of these x plus 1's cancel, leaving me finally with 4 over x plus 1 cubed. The whole point of this is that if I take the derivative, I get a function, and then I think of that as a new function that I then have to take the derivative of again, and I get this function. If this describes the slope of the original function, this will tell me how that slope is changing.